All right, strap yourselves in because today we're going deep, deep into the physics of rotation.
Ooh, I like it. Deep.
Yeah, like a spinning top? Or those twirling dancers.
Even planets around a star. It's all about rotation.
And we're going to go beyond just thinking of things as simple dots.
Right, right. We're
Yeah.
looking at how the shape, the actual size of a rotating thing, you know, affects how it moves.
Yeah, it's not just about how fast it's spinning.
Exactly. It's also how all that spinning energy is like spread out within the object itself. That's where the fun begins.
Totally. Okay, so to get us started, let's talk about these rigid bodies we keep hearing about in physics. What exactly is a rigid body?
So in physics, a rigid body is basically like a system of particles. But the key is the distances between them, they have to stay fixed.
Okay, so in a rigid body, the particles are all stuck together in a specific shape, and that shape doesn't change, right?
Yeah, for the most part. Of course, nothing in the real world is perfectly rigid. I mean, everything bends a little under force.
Right, even something super strong like a steel beam, if you push hard enough, it's going to bend a bit.
Exactly. But for a lot of what we do, we can kind of pretend things stay perfectly rigid. Makes the physics way easier.
So it's a good starting point for understanding more complicated movements.
Absolutely. It's a useful model.
Got it. So how do these rigid bodies move? What kinds of motion are we talking about here?
Well, you've got two basic ways they can move. The first is pure translation. It's basically just sliding. And then there's rotation, spinning.
Okay, I can picture that. Like a book sliding across a table, that's pure translation.
The
Right.
perfect example. Every part of the book is moving together, same direction, same speed.
Got it. What about, say, a ball rolling across the floor? It's not just sliding, it's spinning at the same time, right?
Oh, that's a great one. Rolling is actually both things at once. It's translation, A&D rotation. The ball is moving across the floor, but it's also spinning around its center.
So it's like a combo move. Two types of motion happening simultaneously.
You got it. And here's the big difference. In pure translation, all the parts of the object have the same velocity, but in rotation, they don't.
Right. The points further away from the axis of rotation are moving faster than the points closer in.
Exactly. Think of a merry-go-round. The horses on the outer edge, they travel a much longer distance in one spin than the ones near the center.
Right. Even though they complete one rotation in the same amount of time, their speeds are different because they're covering different distances.
Exactly. So that's the key difference between translation and rotation.
Okay, so we've got a rigid bodies moving and grooving, translating, rotating. But to really get rotation, we got to find the objects, like balancing point, right? And that's where the center of mass comes in.
You're exactly right. The center of mass, we often call it the CM. It's super important for understanding how things rotate. You can think of it as the average position of all the little particles in the object.
Okay, so for something simple and symmetrical like a perfectly uniform sphere, the center of mass would be right smack dab in the geometric center, right?
You got it. But for more complicated shapes, things that are irregular, the center of mass might not be so obvious.
Like a weird lumpy potato or something. How would you even find the center of mass in a case like that?
Well, it gets a little mathy, but the basic idea is you got to consider the mass of each tiny part of the potato.
And how far it is from some reference point, right?
Exactly. It's like each tiny bit of mass is voting on where the center of mass should be, and the votes are weighted by how much mass each bit has.
A weighted average, taking into account both the mass and the position of each little chunk of potato.
Exactly.
Okay, so we can find the center of mass, but why is this point so important for understanding rotation?
Because the center of mass is the key to understanding the object's overall motion, even when it's rotating in all sorts of crazy ways.
So even if an object is spinning like crazy, its center of mass still moves according to the regular old laws of motion, like we learned in high school physics.
Exactly. Think about a baseball bat being thrown. It's spinning end over end, right? But the center of mass of the bat is still following a smooth parabolic path, just like any other projectile. It's like the center of mass is leading the way.
That's amazing.
Yeah.
So even in all that spinning and tumbling, there's still a kind of order, predictability.
Exactly. It's a powerful concept. And to show you just how powerful, imagine a projectile that explodes in midair, like a firework. It breaks apart, flying off in every direction. But you know what? The center of mass of all those fragments, it still follows the original path.
Whoa, that's mind-blowing. It's like there's this invisible point that's immune to all the chaos happening around it.
It really shows the importance of the center of mass. And it's not just useful for projectiles, it's essential for understanding things like the motion of binary stars, two stars orbiting each other.
So by focusing on the center of mass,
Mm.
we can simplify things and understand these complex movements more easily.
Exactly.
Okay, so we've got this idea of rigid bodies. We know how to find their center of mass. But how do we actually describe rotation in a more precise way?
Ah, great question. To do that, we need to bring in a new tool, the vector product, also called the cross product.
Vector products.
Yeah.
I vaguely remember those from math class.
Mhm.
Always seemed kind of mysterious.
They can be a bit abstract at first. It's basically just a way to multiply two vectors and get a third vector, but they're super important for describing rotation.
Okay, I'm ready to give it a shot. Break it down for me. What's the deal with vector products?
All right. Picture two arrows. We call them vectors. Each arrow has a length, right? And it's pointing in some direction. Now, when we take the vector product, it gives us a brand new arrow, a new vector that's perpendicular to both of the original arrows.
Wait, so it's like you're taking two arrows pointing in different directions and you're finding a third arrow that's sticking straight up, like out of the plane they form.
Exactly. And the length of this new arrow, its magnitude, it depends on the lengths of the original arrows and the angle between them.
Okay, I think I'm with you so far. But how do we know which way this new arrow is pointing? Up or down?
For that, we use the famous right-hand rule. Picture pointing your index finger in the direction of the first arrow and your middle finger along the second arrow. Now stick your thumb straight out. It's pointing in the direction of that new vector, the one we get from the vector product.
The right-hand rule. I remember trying to use that in physics class. It always felt a little awkward.
It can feel strange, but it's super useful for visualizing these vectors, especially in 3D space.
Okay, so we can figure out the direction of this new vector with the right-hand rule, but how does all this connect to rotation?
Well, the vector product lets us define things like angular velocity and angular acceleration. They're like the rotational counterparts of linear velocity and acceleration, which we use for motion in a straight line.
So we're starting to see how this kind of abstract math stuff relates to the real world of things spinning around.
Exactly. And once we get a handle on these concepts, we can start to unlock all the secrets of rotational motion. It's pretty cool stuff. So we've kind of laid the groundwork here. Rigid bodies, the center of mass, that vector product thing. Now let's really get into the spin of things. You know what I mean? Let's talk about angular velocity.
Okay, yeah, let's spin it. So angular velocity is basically how fast something is rotating, right? Like how many times it spins around in a minute or something.
You're on the right track. Angular velocity, we use the Greek letter omega for that. It tells us how fast an object's angular displacement changes over time.
Angular displacement. So
Yeah.
it's not just about the number of spins, but the angle it's rotated through.
You got it. Imagine those hands on a clock, right? The minute hand makes a full circle, 360 degrees every hour. So its angular velocity is constant, covering that same angle in the same time.
Okay, makes sense. Angular velocity is about how quickly something is sweeping through those angles as it rotates.
Exactly. And here's where it gets cool. Angular velocity, it's actually a vector.
Hold on, it's not just a number. It has a direction, too.
It does. And, you guessed it, we use that trusty right-hand rule to figure out which way it's pointing. Curl your fingers in the direction of the rotation, your thumb, boom, that points along the axis of rotation. That's your angular velocity vector.
So if a wheel is spinning clockwise, that angular velocity vector would be pointing inwards, like an axle going through the wheel.
Exactly. You're getting it.
Okay, I think I'm starting to see how these vectors work in the world of spilling things. So what about angular acceleration? Is that just how fast the angular velocity is changing?
Bingo. Angular acceleration, we use alpha for that. It tells us if the angular velocity is increasing, decreasing, or staying steady. Speeding up, positive angular acceleration. Slowing down, negative angular acceleration.
So it's like the gas pedal and brake for rotational motion.
Love the analogy.
Okay, so we've got angular velocity and acceleration down. But what actually causes things to rotate? What's the rotational version of like a force pushing something?
That, my friend, is where torque comes in. Torque is the force of rotation. It's what gets things spinning or makes them stop.
Cork. Yeah, I've heard the word, but I don't really get it. It sounds kind of like twisting, wrenching something.
Think about opening a jar, right? That lid is stuck. You're applying a force to the lid, but how much torque you create depends on where you push and in what direction.
Right, like if I push on the very edge of the lid, it's easier to open than pushing near the center, even if I'm pushing with the same strength.
Exactly. Because you're getting more torque when you push further from that axis of rotation, leverage.
So torque is about force, and that distance from the axis of rotation.
You got it. And to get even more precise, torque is actually another one of those vector products we were talking about.
Another one. Okay, walk me through it.
All right, back to that jar lid. There's a position vector. It points from the center of the lid, that's the axis of rotation, out to the point where you're applying the force. Then there's the force vector, pointing the way you're pushing. Torque. That's the vector product of those two.
Okay, so right-hand rule again. Index finger along the position vector, middle finger along the force vector. My thumb points in the direction of the torque.
Nailed it.
So torque is what makes things spin. It's like the rotational twin of force, which makes things move in a straight line.
Exactly. And just like a force can cause acceleration, torque causes angular acceleration, makes things spin faster, slower. You get the idea.
Okay, this is all starting to come together.
Wait, there's more.
Right. Angular momentum. I've heard it's super important for understanding things like, I don't know, figure skaters spinning and planets orbiting stars.
You're right on the money. Angular momentum, it's a big deal in rotational motion. It's like the rotational counterpart to linear momentum. Remember that? It's how much an object wants to keep moving in a straight line.
Right, like a bowling ball. It's got a lot of linear momentum because it's heavy and moving fast, hard to stop.
Exactly. So angular momentum, it's how much something wants to keep rotating. The more it's got, the harder it is to change that spin.
So linear momentum depends on mass and velocity. I'm guessing angular momentum has rotational versions of those.
Spot on. Angular momentum depends on an object's moment of inertia. That's the rotational mass, so to speak, and its angular velocity.
Moment of inertia. Didn't we touch on that earlier?
We did. We'll go into more detail in a bit. But for now, think of it as how much an object resists changes in its spin. And get this, it's not just the object's mass. It's also how that mass is spread out relative to the axis of rotation.
So something heavy and spread out, like with its mass far from the axis of rotation, will have a bigger moment of inertia than something compact with the same mass.
You got it. Think of a figure skater with their arms out spinning.
Yeah.
Their mass is far from their spin axis, so their moment of inertia is large. They pull their arms in closer to the axis, moment of inertia shrinks.
And since angular momentum depends on that moment of inertia, it means their angular momentum changes too, right?
Not so fast. That's where things get really wild. Angular momentum, like its linear cousin, it's conserved, as long as there aren't any external torques messing things up.
Okay, wait, I gotta make sure I'm following. You're saying if there's no outside torque messing with a rotating object, its angular momentum stays the same, even if its moment of inertia is changing.
You got it. It's one of those physics laws, fundamental, explains a ton of cool phenomena.
Whoa, okay. Back to our skater pulling their arms in.
Yeah.
Moment of inertia decreases, right?
Great.
But the angular momentum has got to stay the same, no external torques. So what happens?
They spin faster, their angular velocity increases. It's like this beautiful trade-off. As their moment of inertia gets smaller, their angular velocity has to increase to keep that angular momentum constant.
That's wild. Like this secret dance between moment of inertia and angular velocity, all because of this conservation of angular momentum thing.
It is kind of like a dance, isn't it? And this dance happens on huge scales, too. Explains why planets move faster when they're closer to the sun in their orbits, or how galaxies hold their shapes over billions of years.
Wow, I'm starting to see how powerful this concept is. Connects the spin of a skater to the movements of planets and galaxies. Okay, so we talked about moment of inertia in a general way, but how do we actually calculate it? Some kind of formula.
There is. It involves a bit of calculus, but don't worry, we won't go full math nerd here.
Good, good. I'm more of a concept person.
The basic idea is we look at each tiny bit of mass in the object and how far it is from the rotation axis. Square those distances, multiply them by the mass, and add it all up.
Okay, so each bit of mass is like voting on how hard it is to spin the object, and the further away it is, the more it gets to say.
That's a great way to put it.
So we could calculate the moment of inertia for any object, no matter how weird its shape.
In theory, yeah. But luckily for us, a lot of common shapes, spheres, cylinders, rods, physicists figured out those formulas already. They're in the textbooks.
Ew, good to know. I'm not quite ready to dive into calculus land. What about this radius of gyration thing I've heard about? Is that related to moment of inertia?
It is. The radius of gyration, we often call it K, is a way to make moment of inertia a little easier to think about. Imagine you squished all the object's mass into a single point, but it still had the same moment of inertia. The distance from that point to the axis of rotation, that's the radius of gyration.
So it's like finding the average distance of the object's mass from the axis.
Exactly. Like finding the sweet spot where all the mass could be bunched up and give you the same rotational resistance.
That's a good way to visualize it.
And it turns out for lots of shapes, that radius of gyration has a pretty simple connection to the object's dimensions. Like a solid sphere spinning around its center, the radius of gyration is just the square root of 25 times the sphere's radius.
Interesting. Like a shortcut for calculating moment of inertia for those common shapes.
Exactly. Makes life easier.
Okay, so moment of inertia, radius of gyration, how they relate to angular momentum. Starting to click now. But can you give me a real-world example of how this all works? Something we might actually encounter?
Absolutely. Ever wonder how engines, especially those with pistons, stay smooth, keep that motion going consistently? It's all thanks to this cool device called a flywheel.
The flywheel, yeah. I know it's part of an engine, but I never really got what it does. How does it help things run smoothly?
A flywheel, basically, it's a heavy disc, spins around. It's designed to have a really big moment of inertia.
So it's like a rotational inertia champ, but how does that make the engine smooth?
Well, engines with the pistons, they produce power in bursts, right? Each piston fires, energy jolt, engine speeds up for a moment. But between those bursts, it would naturally slow down. That's jerky, inefficient.
Ah, so the flywheel is like a buffer. Absorbs those bursts, releases them more gradually.
You got it. Because that flywheel has such a large moment of inertia, it resists those sudden changes in speed. It takes a lot of torque to make it spin faster or slower. That's what smooths out those energy bumps from the pistons, makes the motion way more consistent.
Amazing. So the flywheel is using that conservation of angular momentum thing, right? It wants to keep spinning at a constant rate, so it smooths out those sudden changes from the pistons.
Exactly. Perfect example of how we take a simple physics principle and turn it into something really useful.
I'm starting to see flywheels everywhere now. Are they just in car engines?
Car engines for sure, but they're in lots of other machines too. Pottery wheels use them to keep spinning nice and steady. Some power tools use them to store energy, release it in powerful bursts. You even find flywheels on some playground equipment.
Wow, so versatile. Okay, we've covered a ton here. Angular velocity, acceleration, torque, momentum, inertia, that radius of gyration thing, and now the flywheel.
It's been quite the spin. And we've seen how all these concepts apply to so many things, from skaters doing their thing to how engines run smoothly.
Yeah, it's mind-blowing. These kind of abstract principles of rotational motion are all around us in the everyday things we use.
It really is. And we haven't even touched on some of the really wild applications of rotational motion, like gyroscopes or how rotating black holes behave.
Ooh, you're just teasing me now. I guess we'll have to save those topics for another deep dive.
Yeah.
It's crazy to think, right? These same ideas about how a figure skater spins, they apply to, like, those massive clouds of gas and dust that form stars and planets.
It really shows you how connected everything is in the universe.
Yeah.
The laws of physics, they're universal. Doesn't matter if it's something here on Earth or, way out there, billions of light years away.
It's making me see the world in a totally new way.
I get that.
I'm noticing rotation everywhere now.
That's the cool thing about physics. It gives you this deeper understanding of, the everyday stuff. A&D, the vast cosmos.
Totally. So, as we wrap up this deep dive into rotation, is there one last thought you want to leave us with? Something to chew on as we go about our day, seeing the world with this new rotational awareness?
How about this? We talked about how moment of inertia depends on how the mass is spread out, right? Well, that same idea applies to really big rotating systems too. Think about galaxies, those huge collections of stars, gas, dust. Their shape, their structure, it's all influenced by how their mass is distributed, how it's rotating.
So you're saying that the way galaxies look, how they change over time, it's all tied to these same ideas about rotation that we've been talking about.
Exactly.
Yeah.
It's a great example of how these concepts apply not just to, things we can hold, but to the largest structures in the universe.
That's incredible. I'm going to be looking at the night sky differently now. Well, I think we've officially reached the end of our spin through the world of rotation. Hopefully you're leaving with a whole new appreciation for all the spinning going on around us.
And remember, there's always more to discover. The world of physics is full of surprises waiting to be found.
We'll put some links in the show notes if you want to explore further. Until next time, keep those minds spinning.